Hello, in this lecture, we'll define Gauss map on a regular surface. And then we'll study one of its fundamental property. So Gauss map, it arises from a normal vector field. Okay, so let us look into this thing. Let us begin with a regular surface S in R3. And let us take a surface patch for this regular surface S. Okay. So the sigma, it is a differentiable map from U to R3, and sigma of U, it is in S. Okay. So now if I take any point P in sigma U and take this normal vector defined by NP equal to the vector product of sigma U with sigma B divided by norm of sigma U cross sigma B. So this whole thing is evaluated at the point P. So this N P is normal to or orthogonal to the tangent space. Let me draw a picture. So suppose this is my surface S and this is my sigma U, and if I take a point here P, and let us take this TPS to be the tangent plane at the point P. So this NP, it is normal to the surface, meaning that NP is orthogonal to every tangent vectors. Okay. So this NP, it is a vector starting at the point T. And this NP, it is a unit vector. Now, if I take this coordinate axis, and now if I take this normal vector NP, so we parallel translate this vector to a vector starting from the origin. Let us call it to be n bar P. So n bar P, it is a vector starting from the origin. And n bar p is parallel to np. And norm of n bar p is equal to 1. Okay, so therefore, I have a map. So therefore, we have a map n from this U to unit sphere. Okay, so for the sake of notation, so let us first take this to be my n bar. And after translating, let this to be my np. Okay, so n bar p is the unit normal vector starting at the point P, and it is orthogonal to the tangent space TPS. And then we are translating this n bar P to origin to get the vector NP. So this n, so it gives a map from U to the unit sphere. Okay, so this n, it is a map from this U to the unit sphere. Okay, so now let me define Gauss map, which is same as aim. Let me define it formally. So let us take S to be a smooth, regular surface. So in addition to regular, we are taking the surface to be smooth because we want to prove, let us, some properties of this map N. For that, we need smoothness of the surface S. Okay, so what does this smoothness means? So S smooth, so implies for any surface patch, or let me write like this. So a smooth implies S can be covered by surface patches U sigma, where the sigma is a smooth map. That is, all the mixed order partial derivatives exist and continuous. Okay. And let us take this N to be an orientation on S. So let N be an, or N bar be an orientation on S. Okay, so again, what is the meaning of orientation? So n bar S2 R3 is a differentiable unit normal vector field on S. Okay. So we have the same picture. So this is my surface S. Let us take a point P. And if I take the tangent plane TPS, so we have this vector n bar P. And this n bar, we want it to be also differentiable. Okay. And let NP equal to the vector obtained by translating n bar uh, parallelly to origin. Okay, so we'll get a map n from S to S2. The map n is called the Gauss map of S. Okay, and so this n, it will be also a differentiable map because n bar is differentiable. So n bar differentiable, and translation also it is a differentiable map. So therefore n is a differentiable map. Now, if I take the differential of this n, dn p, it is a map from the tangent space of S to tangent space of np S2. Okay. So now, note the following. We can take the tangent space of S2 at the point np to be equal to the tangent space of S at the point P. So why we can do that thing? Let us take this surface S, and this is my point P. And these are my coordinate axes. And I have the unit sphere here. And now at this point P, I have the unit normal vector NP, which is orthogonal to the tangent space TPS. And corresponding to this NP, I have this, so this above thing is N bar P, and corresponding to this N bar P, I have NP here in the unit sphere. So the endpoint of the vector NP, it lies on the unit sphere. And now we can also translate the tangent space TPS. So if I translate the tangent space TPS to here, so I'll get TNP S2. So tangent space of S2 and P will be same as the translation of the tangent space TPS. Okay. So therefore, without loss of generality, we can assume this TNPS2 is equal to TPS. So since T and Q S2 is parallel to, sorry, so this should be TNPS2 is parallel to TPS, we can assume TNPS2 to be equal to TPS. So this differential of this NP, now it is a map from TPS to TPS. So this is a linear operator on the tangent space. So here the target space and the source space are the same. Okay. So let us give two examples of this Gauss map. So let us take this S to be this plane. AX plus BY plus CZ equals to DT. And this N, it is equal to, so N of any point XYZ. So this is equal to A, B, C divided by norm of this vector ABC So therefore it is equal to, so normal to every point xyz belonging to S is equal to the vector ABC divided by root over A square plus B square plus C square. So this N, it is a map from this S to S2. So here this N is a constant map. Okay, so therefore d n xyz is equal to 0 map. Next example, let us take S to be the unit sphere. Yeah, S to be the unit sphere. And now what will be the uh, this Gauss map here? So Gauss map N, it is from this S2 to S2. So here, so check that. So N is an identity map. Okay, so it is clear from the definition that this N, it is an identity map. So this D of N at any point x, y, z. So this is also identity map. Okay. So this differential of Gauss map is called shape operator. The differential of the differential D and P of the Gauss map N S2 S2 is called the shape operator. Okay. So now let me prove one of the property of this shape operator, proposition. The shape operator D and P from tangent space of S at the point P to TPS is a self-adjoint operator. So that is, if I take the inner product of D and P, U W, let us take it to be B. So inner product of D and P U with B, it is equal to U, inner product of U with D and P, P, So for all tangent vectors, UB belongs to TPS. Okay. So here let me denote this UB with different symbol, because UB I'll be using for the surface patch. So let us write DNP W1, comma W2. So this is equal to inner product of W1 with DNP W2. So where this W1, W2 are tangent vectors. Okay. So how to prove this thing? So let us take a surface patch U comma sigma such that P is contained in sigma U. So let U sigma be a surface patch such that P belongs to sigma U. And let us take, so let alpha minus epsilon to epsilon. So, or maybe let me write like this. So let alpha t is equal to sigma ut comma vt, where this t it varies in this interval minus epsilon to epsilon. So alpha 0 is equal to p. So alpha prime 0, it belongs to the tangent space of S, and alpha prime 0 is equal to sigma u du dt evaluated at the point t equals to 0 plus sigma b dv dt. So this is evaluated at the point t equals to 0. Okay. And now we will be applying d and p on this alpha prime 0. So this will be equal to d and p sigma u dudt at the point t equals to 0 plus d and p sigma b dv dt at t equals to 0. So this equality hold because d and p, it's a linear map. So we are using this linearity of this map d and p. So since d and p is linear, okay. So therefore, uh, so du dt at the point t equals to 0, it is u prime 0, so which is a scalar. So again, you apply linearity. So what you'll get, u prime 0 and dnp of sigma u. So by the chain rule, so what you'll get, it is del u of n compose sigma plus b prime 0 del b of n compose sigma. So let us take nu to be equal to del u of n compose sigma and nb to be equal to del b of n compose sigma. So therefore what we have, dnp of alpha prime 0 is equal to u prime 0 and U plus B prime 0 and B. Okay. So we have this thing here. And now let us take two vectors. So let W1, W2, it belongs to the tangent space of S, and W1 is equal to alpha prime 0. Okay. So we know that sigma U, sigma B is a basis of the tangent space TPS. So this W1 I can write as the follows. So W1 equals to C1 sigma U plus C2 sigma B. And W2 is equal to D1 sigma U plus D2 sigma B. So this we can write. Okay. And now we apply this DNP on this W1. So DNP of W1, so this is equal to the inner product, no, sorry, you apply linearity, so it is equal to C1 DNP sigma U plus C2 DNP sigma B. So which is equal to C1 NU plus C2 NB. Okay. So now if I take this inner product DNP W1 with W2, so I'll get, so this is inner product of C1 and U plus C2 and B, comma D1 sigma U plus D2 sigma B. And if I expand this, so it will be equal to C1 D1 inner product NU sigma U plus C1 D2 inner product NU sigma B plus C2 D1 inner product NB sigma U plus C2 D2 inner product NB comma sigma B. And similarly, if I take the inner product of W1 with DNP W2, so we'll get this is equal to C1 D1 sigma U inner products of sigma U and U plus C1 D2 inner product of sigma U with NB plus C2 D1 inner product of sigma B with an U plus C2 D2 inner product of sigma B with NB. Okay, so now here note that this inner product is same as this inner product and this inner product is same as this inner product. Okay, and now if I prove that inner product of NB sigma U is same as inner product of sigma B and U, if I show this thing, so then Then again, using the same kind of argument, inner product of nu sigma b will be same as inner product of sigma u and b. Okay, so if I show these things, so then this two inner product will be same. Okay, so it suffices to show inner product of sigma u and b is same as inner product of nu comma sigma b. Okay. So let us take, so let f p to be equal to inner product of this np. So n was this Gauss map. So np with sigma b at the point p. Okay. So n is orthogonal to, np is orthogonal to the tangent vector. So in particular, it will be orthogonal to sigma bp. So this will imply that fp is equal to 0. So f is a constant function on S. So f is constant on S. So therefore, if I take the partial derivative of f with respect to u, so that will be also equal to 0. So 0 equal to, so fu, so this is equal to inner product of nu comma sigma b plus inner product of n comma sigma ub. So all these partial derivatives are computed at the point t. So from here, so what we have, n u sigma b is equal to minus n comma sigma ub. And let us take gp to be equal to inner product of np with sigma up. So again, so because np is normal to sigma u, so this will be equal to 0. So g is constant on S. So therefore, the partial derivative of g with respect to b is equal to 0. So 0 equal to gb. So this will be equal to nb comma sigma u plus nb comma sigma, sorry. So this will be inner product of n with sigma ub. So therefore, inner product of nb comma sigma u is equal to minus n comma sigma ub. Yeah, so here this partial derivative, here it should be sigma b u, sigma b u here. So therefore from 1 and 2, so what I'll get is the following. Yeah, so you have to use another fact. So sigma UB is equal to sigma BU as all these partial derivatives are continuous, as mixed order partial derivatives are continuous since S was assumed to be a smooth surface. Since S is a smooth surface. So now from 1 and 2, so what you'll get, the inner product of NB comma sigma U is equal to inner product of NU comma sigma B. Okay, so therefore we are done. So this shows that DNPW1, this inner product of DNPW1 with W2 is equal to the inner product of W1 with DNPW2. Yeah, so this shows that DNP, it is a self-adjoint operator. Okay, so we'll continue in the next class.